Welcome to AudioCert, where the official study guides are brought to life. And today we're diving headfirst into a module that's absolutely foundational for anyone looking to understand how networks are explored and secured. Scanning networks. Okay, let's unpack this crucial cybersecurity territory. Our mission on the deep dive is, well, to cut through the complexity of study material and deliver truly insightful, digestible knowledge, giving you those real aha moments.
Absolutely. And what's fascinating here, and I think often misunderstood, is that scanning isn't the intrusion itself. Instead, it's an extended, much more aggressive form of reconnaissance. Think of it as the detailed intel gathering phase after you've done some initial passive observation.
Footprinting, right?
Right after footprinting. It's when our, let's say, digital detective starts actively probing, discovering crucial details like operating systems, specific services running on those systems, and any potential configuration lapses. It's building a comprehensive profile of the target before even contemplating an entry.
Exactly. Sometimes people jump straight to hacking without realizing the sheer amount of groundwork involved, all that prep work. Our mission today is really to give you a shortcut to being genuinely well-informed about network scanning. By the end of this deep dive, you're not just going to know what network scanning is, but why these techniques are used, how the tools work, and even the clever ways ethical hackers and attackers try to evade detection. We want you to walk away with a clear strategic picture.
And to help us achieve that clarity, we'll be pulling directly from the EC Council Certified Ethical Hacker, or CEHv13 Module 3 scanning networks. That's our source material. Our key objectives for you today are pretty straightforward, but the insights, I think, are profound. We're going to help you grasp the core network scanning concepts, master the various techniques for host, port, service, and operating system OS discovery, and, crucially, understand how to scan beyond intrusion detection systems, or IDS, and firewalls. We'll also touch on network scanning countermeasures, the defensive side, and we're committed to using vivid, real-world analogies, clearly spelling out all those pesky acronyms, and providing practical examples to ensure these complex ideas really stick. Hopefully give you some genuine strategic takeaways.
Okay, sounds like a plan. So let's kick things off by laying down the foundation. In our previous discussions about footprinting, we talked about it as that initial, somewhat passive phase of hacking. It's where attackers gather primary high-level information like domain names, IP ranges, public records, that kind of broad intelligence, sort of looking from the outside in.
Right. Footprinting is like getting a general overview, maybe a satellite image of the landscape. Scanning, however, directly builds on that. It takes that initial high-level information and drills down, moving into what the source material describes as highly complex and aggressive reconnaissance techniques. It's a significant shift from just observing a building from a distance to, well, actively knocking on every window and door.
That's a great way to put it. So, at its core, how would you define network scanning, and maybe more importantly, what's the strategic goal behind it for someone who's, already familiar with the basics? Why do we do it?
Fundamentally, network scanning is a set of procedures used for identifying hosts, ports, and services in a network. Pretty simple definition. But the why is key. It's not just a technical exercise. Its purpose is to build a detailed, almost forensic profile of the target organization. We're talking about identifying active machines, figuring out the specific operating system, the OS running on those machines, and then, crucially, mapping out all the services running on those systems. It's like a scout charting unknown territory. But now, they're not just looking for points of interest. They're trying to identify every path, every potential weakness, and every resource available, really trying to understand the personality of the network.
And when we talk about the process, it's often oversimplified, isn't it? Like attacker sends TCP IP probes, gets network information. But that simple loop hides a lot of strategic complexity. It's not just a technical ping-pong match.
Absolutely not. It's a carefully orchestrated conversation, often very subtle, designed to elicit specific responses from the target. To use a more tangible analogy, imagine you're trying to figure out what's inside a large, unfamiliar building. Footprinting is like looking at the building from the outside, noting its address, general size, maybe how many floors it has. Scanning, on the other hand, is much more active. It's actually going up and knocking on every single door and window, listening intently for sounds, seeing which one's open, and trying to peek inside to see who's there, what they're doing, and maybe what kind of security is in place. Those TCP IP probes are essentially your carefully crafted knocks and observations, designed to elicit specific responses that tell you volumes about what's inside.
Okay, that makes a lot of sense. So for both ethical hackers aiming to secure a network and, well, malicious actors looking to exploit it, why bother with all this detailed scanning? What are the truly critical objectives they're trying to achieve with this active probing?
Well, the strategic objective is pretty simple, really. The more information an attacker has about a target, the higher their chances of finding security loopholes and ultimately gaining unauthorized access. The source outlines several critical goals here. First, discovering live hosts that's active computers along with their Internet Protocol or IP addresses and, crucially, their open ports. This helps determine the most promising entry points.
Finding the open doors.
Exactly. Second, identifying the specific operating systems, the OS, and the system architecture. This is also known as fingerprinting. Knowing the OS allows attackers to tailor their strategies based on known vulnerabilities that affect that specific system. Different exploits for Windows versus Linux.
Makes sense.
Third, pinpointing the services running on those hosts, which can reveal specific weaknesses related to outdated or perhaps misconfigured software. Fourth, directly identifying vulnerabilities within those live hosts, sometimes through banners or specific responses the services give back. And finally, creating a detailed map of the network topology. So understanding all the devices, routers, switches, and how they're interconnected. This comprehensive map is invaluable for planning an attack or, if you're a defender, understanding your entire infrastructure of potential attack paths.
So for you, our listener, understanding these details isn't just academic. It's truly crucial for either identifying a network's security loopholes or, conversely, developing robust defense strategies. It's foundational knowledge. Now, network scanning sounds like a big umbrella term. Are there different flavors of scanning we should be aware of? What's the strategic difference between them?
There definitely are. And the source breaks them down into three main types, each with a distinct strategic focus. First, we have port scanning. This focuses on checking the services running on the target computer by sending a sequence of messages. The goal isn't just to see if a port is open, but to identify which services are in a listening state, because that state provides crucial information about the OS and the applications in use. To use our building analogy again, this is like trying every single doorknob on a building. Which ones are unlocked? Which ones lead somewhere interesting, like, I don't know, the server room or a public reception area?
Right, and it's not just about what's open, but what's listening on those open ports, right? Because sometimes those active listening services might have misconfigurations or known software vulnerabilities, making them prime targets.
Exactly. A single misconfigured service on an open port is often way more valuable to an attacker than dozens of closed ports. It's about quality, not just quantity. Then there's network scanning, which, in this more specific context, is focused on identifying active hosts and IP addresses on a network. This is more of a foundational roll call, simply figuring out who's actually home in the neighborhood, which machines are currently online and responding. It's like taking an inventory of all the houses on the street before you even consider knocking on doors.
Okay, makes sense. And finally, we have vulnerability scanning, which really narrows the focus, sounds like.
Yes. Vulnerability scanning is a method for checking whether a system is exploitable by identifying its known weaknesses. A vulnerability scanner typically consists of two main components: a scanning engine that performs the checks, and a constantly updated catalog of known vulnerabilities. This catalog is essentially a massive database of common flaws, misconfigurations, and known exploits. So this isn't just seeing if a door is unlocked, it's identifying that the specific brand and model of the lock itself is old, maybe rusty, and known to be easily picked. It's much more targeted at specific exploitable flaws.
That thief breaking into a house analogy from the source material really resonates here. The ports are the doors and windows, and while generally more open ports mean more vulnerability, well, it's not always about quantity, is it? Sometimes a system with fewer open ports can be even more vulnerable if those specific critical ports house unpatched services. It's not just about the number of exposures, but the quality of that exposure. One critical outdated service can expose an entire network.
Precisely. A single critical, vulnerable service on an otherwise closed system can be far more dangerous than many low-risk open ports. It's about understanding the context and the potential impact of each open door, each potential vulnerability.
Okay. And to actually do all this sophisticated scanning, you need some serious tools in your ethical hacker toolkit. What are some of the primary ones we'll be exploring today?
Yeah, the primary tools that attackers, and of course ethical hackers, use for network scanning are quite diverse and powerful. We'll definitely be looking at Nmap, or Network Mapper, which is arguably the most versatile and widely used scanner out there. We'll also touch on CEHv13, which is a really powerful packet crafting tool for more customized scans. Then there's Metasploit, which is a whole framework for penetration testing, but includes powerful scanning modules. And also NetScan Tools Pro, a comprehensive suite for network diagnostics and discovery. Nmap really excels at host discovery, port scanning, OS detection, and even version detection. CEHv13 gives you that fine-grained control over crafting and sending custom packets, which is crucial for stealthier scans or testing specific responses. Metasploit, while a full framework, has excellent auxiliary scanning modules, and Netscan Tools Pro offers a range of integrated tools for troubleshooting and discovery, kind of an all-in-one toolbox. We'll delve into how these work and, maybe more importantly, why you'd choose one over the other for specific strategic goals shortly.
Right. But before we dive deeper into how these powerful tools work, we need to quickly recap the fundamental building blocks of network communication, especially when it comes to Transmission Control Protocol, or TCP. It's a connection-oriented protocol, meaning it prioritizes establishing a stable connection before any data can be transferred. Understanding this is absolutely key to understanding how scanning techniques are engineered.
That's right. Every TCP packet has a header, and within that header are various flags that essentially control the conversation between hosts. They manage the connection state. There are 6 specific TCP control flags, each represented by a single bit. When a flag's value is set to 1, it means that flag is on or active. Think of these flags as the different nonverbal cues or gestures you'd use in a conversation. Maybe a nod to initiate, a raised eyebrow to confirm, a hand wave to pause, or maybe a shrug to end a discussion. The brilliance of scanning is in manipulating or observing these flags, often in unexpected ways.
Okay, let's quickly run through the most important ones for our discussion today. First up, SYN, or synchronize.
Yeah.
What's its primary role in this digital conversation?
SYN's main job is to signal a request to synchronize sequence numbers and, crucially, initiate a connection. It's essentially the opening volley, like asking, hey, are you open to talk? In a digital sense. It starts the whole process.
And then we have ACK, or acknowledgement,
Yeah.
the confirmation signal.
Exactly. ACK confirms the receipt of a transmission and identifies the next expected sequence number. When a system successfully receives a packet, it sets its ACK flag to 1, essentially saying, yep, I got it and I'm ready for the next piece. It's absolutely crucial for reliable data transfer in TCP.
Got it. Next, FIN for finish.
Yes.
Seems self-explanatory.
It is. When FIN is set to 1, it announces that no more transmissions will be sent to the remote system, indicating that the connection is being politely terminated. It's the digital equivalent of saying, okay, I'm done talking now, let's wrap this up gracefully.
And finally, RST, or reset. This one sounds a bit more forceful, maybe abrupt.
It is. The RST flag is set to 1 when there's an error or maybe an unexpected packet arrives in the current connection, aborting the connection immediately and forcefully. It's like saying, whoa, something went wrong, stop this conversation immediately, no graceful goodbye here. And the source specifically notes that attackers use this flag, RS2, to scan hosts and identify open ports because a server's response, or sometimes lack thereof, to a crafted RST packet can reveal a lot. We'll definitely see how in a moment.
Right. So it's truly the clever manipulation and observation of these SYN, ASA, FIN, and especially RST flags that are critical for gathering that illegitimate information from servers, as the source puts it, sometimes without even completing a full connection, which is key for stealth.
Indeed. Now, all these flags work together in a very specific sequence known as the TCP Three-Way Handshake. This is an absolute cornerstone of TCP communication and is fundamental to understanding many, many scanning techniques. It's basically a polite, structured digital negotiation to start talking.
Okay, so how does that negotiation actually happen in practice? Let's walk through it.
Okay, imagine a client, let's say its IP address is 10.0.0.2, trying to reach a server at 10.0.3 on a specific port, maybe port 21 for FTP. The client first sends a SYN packet to the destination server. This is its way of saying, hello, I want to establish a connection. Are you listening on port 21 and ready?
And what's the server's response if it is listening on that port?
If the destination server is indeed listening on that port, it responds by sending a SYNEC packet back to the source client. This is the server essentially saying, yes, I heard you, I acknowledge your request, that's the ACK part, and I'm also sending my own SYN to initiate my side of the connection. It's a two-way agreement starting.
Okay, makes sense.
Yeah.
And for the final step of the handshake, to seal the deal.
The client then sends a final ACK packet back to the server, specifically acknowledging the server's SYN packet. This completes the three-way handshake, and an open connection is established, allowing full two-way communication to proceed. And understanding this handshake is absolutely vital because, as we'll see, many scanning techniques exploit or mimic parts of it to gather information without fully establishing that connection. That's where the stealth often comes in.
Right, and just like a digital conversation needs to start politely, it also needs to terminate gracefully, usually.
Yeah.
How does a TCP session typically end?
Well, After all the data transfers are complete, either side can initiate the termination process by sending a FIN, or finish, a packet, like saying, I'm done. The other side acknowledges this by sending an ACK. Then, the second party usually sends its own FIN packet to signal it's also done sending data. And the first party sends a final ACK to acknowledge that. This organized four-way exchange ensures all data is accounted for and the connection is cleanly closed. It's like an organized way to say goodbye and hang up the phone properly. Sometimes, however, as we mentioned, an unexpected RST can terminate a connection forcefully, cutting it short.
All right, so we've got the language of TCP down the flags, the handshake, the termination. Now let's put it into action. The first big strategic task in network scanning is host discovery, simply figuring out which systems are alive and responding on the network.
Right.
You don't want to waste time knocking on doors if nobody's home, right?
Precisely. This is absolutely foundational for efficiency. You really don't want to waste cycles, time, and generate unnecessary noise trying to scan every single port on systems that aren't even online. Host discovery gives you an accurate status of the systems in the network, enabling you to focus your efforts much more efficiently, avoiding those noisy and ultimately futile attempts on inactive targets.
Okay. And for many of these techniques, Nmap, Network Mapper, is really the go-to tool. The source even shows screenshots from Nmap, which is Nmap's graphical interface, making it a bit more user-friendly for some. Let's break down some of the key host discovery techniques, starting with an ARP ping scan. This one's particularly interesting for local networks, isn't it?
Yeah, an ARP ping scan is very effective locally. It utilizes Address Resolution Protocol packets, that's ARP, to discover active devices on a local area network, or LAN. What's ingenious about this is that it works at a lower network layer, layer 2, which means it can often work even when devices are hidden behind restrictive firewalls that might block higher-level IP pings, like ICMP. When an operating system needs to send an IP packet to a target on the same LAN, it first needs to know that target's MAC, or Media Access Control, address. It does this by sending an ARP request to the entire segment, basically asking who has this IP. If the host with that IP is active, it will send an ARP response back, essentially saying, I'm here and here's my unique MAC address. The Nmap command for this is nmap-sn-pr target IP. Here, ARP-SN disables the port scan, we only want host discovery, and -pr specifically tells Nmap to use an ARP ping.
So it's kind of like shouting out who has the key to address X on this specific street. Only the person with that key on that street will shout back their name, or in this case, their unique hardware address, their MAC address. It's localized and very efficient for LANs.
Exactly. Its advantages include being much more efficient and accurate for LANs because it doesn't rely on higher layer protocols or routing. It handles retransmission and timeouts well, it's useful for scanning large local address spaces quickly, and it can even display the response time, giving you an idea of network latency.
Okay. Next, a UDP ping scan. Now this sounds like it could be tricky given UDP's connectionless nature. How does that work for host discovery?
Right. With the UDP ping scan, Nmap sends user datagram protocol, or UDP, packets to a default, usually uncommon port on the target, like port 40,125. This is where it gets clever. If the target host is active and that specific port is closed, it'll typically return an ICMP, Internet Control Message Protocol, port unreachable message. That message confirms the host is alive. However, if the port is open, no message is returned. If the target is offline or completely unreachable, you might see various other ICMP error messages like host network unreachable or maybe time to live, TTL exceeded. The Nmap command is nmap-sn-pu target IP with an NFPU specifying the UDP ping.
Okay, so it's like tossing a message in a bottle at a specific window. If the bottle bounces back with unreachable written on it, you know the window or port is closed, but crucially the house is there. But if the bottle just disappears, the window could be open and silently accepting it, or maybe there's just nobody home at all. That ambiguity is a challenge, I guess. But the fact it bypasses some TCP filtering is the strategic advantage, right?
Precisely. That's the key advantage. It can often detect systems that are behind firewalls with very strict TCP filtering rules, but maybe they're a bit more lax on UDP traffic. It offers an alternative path for discovery when TCP might be blocked.
What about the classic ICMP echo ping scan? Everyone's familiar with just pinging something using the command line to see if it's alive.
Yeah, the ICMP echo ping scan is indeed the classic ping. It involves sending ICMP echo requests. If the target host is alive and configured to respond, it returns an ICMP echo reply. Simple as that. The Nmap command is nmap Nmap-SN-PE target IP, where JARS-PE stands for ICMP echo ping. This is your standard "Are you there?" signal, much like a sonar ping. It's generally effective on UNIX, Linux, and BSD systems, but it's crucial to note, as the source points out, that it generally doesn't work on Windows-based networks for broadcast addresses due to how their TCP/IP stack implementation handles broadcast ICMP probes. They usually don't respond to those.
Okay, good distinction. So how do you scale that classic ping up to an entire network, taking a roll call of all the machines in a subnet efficiently? That's where an ICMP echo ping sweep comes in, I assume.
Yes, exactly. A ping sweep involves sending ICMP echo requests to an entire range of IP addresses, or a whole subnet, to find all the live hosts within that range. Active hosts will then return an ICMP echo reply, just like a single ping. The Nmap command for this is Nmap-SN-PE IP range. You just specify the range instead of a single IP. The basic pin utility, as you probably know, sends small, typically 64-byte packets and measures the round-trip time. When you ping sweep with Nmap, you're essentially taking that roll call efficiently. Ethical hackers often use subnet mask calculators first to identify all possible hosts in a target subnet before performing a ping sweep to create an inventory of the active systems.
Got it. Now, beyond the standard echo ping, the source mentions a couple of other interesting ICMP ping scans, ICMP timestamp ping scan and ICMP address mask ping scan. What's the strategic advantage of using these, especially if standard echo pings might be blocked by a firewall?
Right. These are clever alternatives designed specifically for situations where traditional ICMP echo pings, type 8 requests, might be blocked by firewalls or IDS. And ICMP timestamp ping scan queries using an ICMP timestamp message, type 13, to try and get current time information from the target. If the target is alive and configured to respond to this type of query, it sends a timestamp reply, type 14. The Nmap command is Nmap-SN-PP target IP with -PP for timestamp ping. Similarly, an ICMP address mask ping scan sends an ICMP address mask query type 17 to acquire subnet mask information. The target responds with its subnet value, type 18, if it's configured to do so. The Nmap command for this is Nmap-SN-PM target IP using -PM for address mask ping. Both are effective techniques for identifying active hosts when the standard echo ping, type 8, is filtered out, simply by using different, less commonly blocked ICMP message types. It's about trying alternative signals.
Okay, that makes sense. Trying different doors, essentially. Now, moving into TCP-based host discovery, we have the TCP SYN ping scan. This one, as we discussed with the flags earlier, sounds like it's built for stealth.
It absolutely is. The TCP SYN ping scan probes different ports by initiating just the first step of a half-open TCP handshake. The attacker sends a SYN packet. If the target port is open and listening, the target sends back a SYNAC packet, just like in a normal handshake. At this point, the attacker knows the host is active and the port is open, so they immediately send an RST packet to terminate the connection before the final ACK is sent. This prevents a full connection from being established and, crucially, avoids leaving full connection logs on the target, making it much stealthier than a full connect scan. If the port is closed, the target responds with an RST packet directly, which also confirms the host is alive. The Nmap command is Nmap-SNSPS target IP with -PS for SYN ping.
So it's like a quick, hello, are you there at a door? If you get any kind of response, even a go away, RST, you know someone's home. But if they start to open the door, SYNAC, you immediately say, never mind, before the door fully opens and anyone can clearly see you or log your full interaction. It's designed to be subtle and fast.
Exactly, and because you don't wait for timeouts on non-responsive ports, machines can be scanned in parallel, making it quite fast, too.
Okay. And a variation of this, which plays another clever trick, maybe specifically on firewalls, is the TCP ACK ping scan. How does this one differ?
Right. The TCP ACK ping scan is similar in its evasive intent, but instead of sending a SYN packet to initiate, the attacker sends an empty ACK packet to a specific port. Now, since there's no prior connection established, the target system, if it's active, should respond with an RST packet to terminate this unexpected out-of-state ACK packet. The reception of this RST packet indicates the host is active. The Nmap command is Nmap-SN-PA target IP using NHPA for ACK ping. The strategic advantage here is that stateful firewalls are often heavily configured to track connection states and might block unsolicited SYN pings trying to initiate new connections. An ACK probe, however, might sometimes bypass these firewall rule sets more easily because an unsolicited ACK is less often seen as an attack signature in some older or less sophisticated IDS firewall rules. It's probing the firewall's logic.
Got it. Trying to slip past the stateful inspection. And finally, for host discovery, an IP protocol scan. This sounds like Nmap just throws everything at the wall to see what sticks, protocol-wise.
Ah, That's a fair assessment. The IP protocol scan sends IP ping packets, but instead of just ICMP or TCP UDP, it sends packets with the IP header specifying different protocol numbers. By default, Nmap sends multiple IP packets using different protocols like ICMP Protocol 1, IGMP Protocol 2, and IP in IP Protocol 4. The hope is that any response from the target to any of these probes, regardless of the protocol used, will indicate the host is online. It's a broader approach to discovery, useful when more specific pings based on TCP, UDP, or ICMP might be filtered out. The Nmap command is nmap-sn-po target IP using LBP protocol ping.
Okay, fascinating range of techniques just for finding live hosts. But here's where it gets really interesting, I think. Artificial intelligence is fundamentally changing the game for ethical hackers and attackers alike. We've seen how powerful Nmap is, but constructing those commands can be tricky. AI can make it even more accessible, efficient, and maybe even more sophisticated, right?
Absolutely. This is a huge development. Attackers, and of course ethical hackers, can now leverage AI-powered tools like ChatGPT or similar large language models to generate highly specific Nmap commands. This effectively automates complex host discovery tasks and lowers the barrier to entry significantly. You don't need to memorize every single Nmap flag anymore. For example, you could just prompt an AI, scan the target network 10.1.1.024 for active hosts, and place only the IP addresses into a file called scan1.txt.
And what kind of Nmap command would that likely generate? Something pretty complex, I bet. It would probably give you a robust single-line command like this. Nmap-sn10 10.1.1 danevo24-og oka upprint $2 scan1.txt. Let's break that down quickly. -sn performs that fast ping scan, no port scan. 10.1 but 1.024 is our target IP range in CIDR notation. -oj outputs the results in a greepable format, which is easy for scripts to parse. Then the pipe sends that output to the awk command. Awk upprint $2 filters for lines ending in up, meaning the host is active, and prints just the second field, which is the IP address. And finally, scan1.txt redirects that filtered output directly into the file. Imagine having to construct that perfectly every time, especially if you're new to Nmap or awk.
Yeah, that's a lot of power and specificity packed into one command, and it cuts down on a huge amount of manual parsing or scripting. Then you could follow up with another AI prompt, couldn't you? Like maybe run a fast but comprehensive Nmap scan against the host listed in scan1.txt, keep it quiet, and write the results to scan2.txt.
Precisely. You could feed the output of the first step right into the next. The AI would then likely generate something like Nmap -t4 ngil scan1.txt on n scan2.txt-v0. Here, -t4 sets an aggressive timing template for faster performance. T4 is aggressive. -il scan1.txt tells Nmap to read the target IPs directly from the scan1.txt file we just created. -on scan2.txt saves the output in normal human-readable format to scan2.txt, and -a0 sets a very low verbosity level, so you only see errors and critical output, keeping the console clean. This dramatically speeds up the process for ethical hackers by making these complex command constructions accessible and automating the initial information gathering. It allows them to focus on analyzing the results rather than wrestling with command syntax.
That's a huge efficiency gain. Now, beyond Nmap and maybe CEHv13, are there other popular tools ethical hackers might use specifically for these ping sweeps? The source mentioned a few.
Yes, the source lists several others that are quite popular for various reasons. These include Angry IP Scanner, SolarWinds Engineers Toolset, NetScan Tools Pro, which we mentioned earlier, Colosoft Ping Tool, Advanced IP Scanner, and Oputils. Angry IP Scanner, for instance, is particularly notable for its multi-threaded approach. It fires off pings very rapidly in parallel, which significantly speeds up scanning of large IP ranges compared to single-threaded tools. It can quickly resolve host names, determine MPO addresses, scan ports, and even gather NetBIOS information like computer names, workgroup names, and sometimes currently logged-in Windows users. Plus, it can save results in various formats like CSV, TXT, XML, or simple IP port lists, offering a lot of flexibility in how you use the gathered intelligence.
Okay, good to know there are alternatives with different strengths.
Right.
So once you know who's home, which hosts are active, the next logical strategic step is to see what doors are open and what's potentially behind them. That's port and service discovery. And this is where the real vulnerability hunting often begins, right? Finding those potential entry points.
Exactly. This phase serves a critical dual purpose, depending on your perspective. Network administrators use it meticulously to verify their security policies, making sure only absolutely necessary ports are open according to their rule set. Attackers, on the other hand, use it to find precisely those open ports and the services running on them, with the clear intent of compromising those services. And it's surprising how often users or even admins unknowingly leave unnecessary ports open, perhaps from old services or misconfigurations. These create easy entry points that attackers are constantly actively looking for. It's an often overlooked source of significant vulnerability.
Yeah, and you might be surprised how many common services operate on specific well-known ports. It's like knowing the front door number for common businesses, but maybe also knowing which of those businesses are notorious for leaving their back door unlocked or a window open. Could you highlight some intriguing examples from the extensive list in the source? Maybe tell us why they're particularly significant finds for an ethical hacker.
Certainly. Knowing these common ports isn't just about memorization, it's about immediately understanding potential weaknesses or the role of a discovered host. For example, finding port 21 TCP open usually means File Transfer Protocol (FTP) is running. While still widely used, it's often deployed for unencrypted transfers, meaning credentials and data can be easily sniffed from the network traffic. That makes it a prime target for passive interception if found.
Okay, unencrypted is always a red flag.
Definitely. Then there's port 22 TCP for secure shell. SSH. Now, SSH itself is secure for remote access when configured properly, but if it's misconfigured with weak passwords, uses outdated encryption, or is exposed directly to the internet without proper controls like IP filtering or failed to patch it, it becomes a crucial, high-value entry point for brute force or credential stuffing attacks.
Right, what about Telnet? That sounds old school.
It is, and finding port 23 TCP for Telnet open is a significant red flag. This is an older, unencrypted remote access protocol. If you find this open, it's a definite security concern because all communication, including usernames and passwords, is transmitted in plain text across the network. Very easy to sniff.
Yikes. Okay, what else? Email.
For email, we have port 25 TCP for Simple Mail Transfer Protocol, SMTP. Finding this open usually means you're looking at an email server. This is critical infrastructure, but if not secured properly, it could be vulnerable to spam relaying, information disclosure, or even denial of service attacks.
DNS, the Internet's phone book.
Port 53 TCP and UDP is for Domain Name System, DNS. Again, critical infrastructure. Vulnerabilities here, like open resolvers or zone transfer misconfigurations, can lead to DNS cache poisoning, redirection attacks, or enumeration of internal network structure.
And the web. HTTP and HTTPS?
Of course, the backbone of the modern web. Port 80 TCP and UDP for HTTP, unencrypted web traffic, and port 443 TCP for HTTPS, encrypted web traffic. Finding these open means you're almost certainly looking at a web server, which immediately points to a whole vast category of potential web application vulnerabilities, SQL injection, cross-site scripting, file inclusion, etc.
Right. What about Windows-specific stuff? NetBIOS, RDP.
Good ones. Finding port 139 TCP and UDP open often indicates the NetBIOS session service is running, which is heavily associated with older Windows networking. This can sometimes reveal system names, workgroup information, and potentially lead to enumeration of weak network shares. SMBCIFS on port 445 is more common now, but 139 is still around. And a very common and frequently targeted port, especially crucial for remote administration Windows systems, is port 3389 TCP. This is for the Remote Desktop Protocol, RDP, or MSWBT server. If this port is exposed directly to the internet, it's a huge flashing target for brute force password attacks or exploitation of known RDP vulnerabilities. It's one attackers scan for constantly.
Wow. Okay, so for you, our listener, understanding these common ports helps you quickly identify not just what a system might be doing based on the services it offers, but also where specific, well-known weaknesses might lie, even before you launch a detailed vulnerability scan.
Yeah.
It's really about building a preliminary threat model based on those open doors.
Absolutely. It helps you prioritize your efforts as an ethical hacker, focusing on the most likely or potentially highest impact entry points first. It guides the next steps.
Okay, now TCP scanning itself is where things get really sophisticated, moving beyond just simple pings or checking default ports. We're going to explore several methods, from the most straightforward, maybe even noisy, to the highly stealthy, each designed to elicit specific information or bypass defenses. Let's start with maybe the most reliable, but also most obvious, TCP Connect Full Open Scan. What's the trade-off here? Why use it if it's noisy?
The TCP Connect scan is indeed one of the most reliable forms of port scanning, but it comes with a significant trade-off. It lacks stealth entirely. It works by completing a full three-way handshake, SYN, SIMASEC, then ACK, to establish a complete TCP connection, just like a normal application would. Once that connection is confirmed as successful, the scanner immediately sends an RST packet to tear it down, but not before the connection is fully established and, crucially, logged on the target system by the operating system and potentially applications. It typically uses the operating system's built-in connect system call to attempt to open a connection to every port of interest on the target. The Nmap command for this is nmap-st target IP.
So this is like knocking, waiting for the door to open, maybe stepping inside, greeting the person, having a full, albeit short, polite conversation, and then saying, oops, wrong house, and leaving. It's obvious, and it definitely leaves a trace in the building's visitor log.
Precisely. That's a perfect analogy. The main drawback is that it's easily detectable and filterable by intrusion detection systems, IDS, and firewalls, because it creates these full logged connections. Any decent logging system will see it plain as day. However, its advantage is that it's highly reliable. If the connect call succeeds, the port is definitely open. Also, it doesn't usually require special super user privileges to run, unlike some stealthier scans that need raw packet access. So sometimes it's the only option if you lack root and min rights.
Okay, so reliability at the cost of stealth. To be a bit more subtle, ethical hackers might employ a stealth scan, also known as a half-open or SYN scan. This is where that clever manipulation of the TCP handshake really comes into play, right? Avoiding the full connection.
Absolutely. A stealth scan, or SYN scan, is designed specifically to be sneaky by exploiting the nature of the three-way handshake, as we discussed. It involves sending just a SYN packet, the first step. If the target port is open and listening, the target responds with a SYNEC, the second step. But crucially, instead of completing the handshake by sending the final ACK, the third step, the attacker immediately sends an RST packet to abort the connection. This prevents a full connection from ever being established and, significantly, avoids triggering the logging mechanisms that typically record completed connections. This makes it much harder to detect. If the port is closed, the target responds with an RST packet directly, which also tells the scanner the port status. The Nmap command is nmap-ss target IP-ss for SYN scan.
So this is literally like knocking, and if someone starts to answer SYNEC, you immediately back away before they can clearly identify you or fully log the interaction. It's designed specifically to bypass firewall rules and logging mechanisms by leaving connections deliberately half open. Brilliant in its simplicity, really.
Exactly. It attempts to hide itself under the appearance of regular, perhaps slightly buggy or interrupted network traffic. It's the default scan type in Nmap when run with sufficient privileges for a reason. It's often the best balance of speed, reliability, and stealth.
Okay, and then things get even more unusual and, frankly, obscure with inverse TCP flag scans.
Yeah.
This category includes things like FIN, XMIS, and ELL scans. These sound like they're playing a completely different kind of game with the flags.
They are indeed playing a different game. These techniques involve sending probe packets with deliberately unusual or unexpected TCP flag combination set. For instance, a FIN scan sends a packet with only the FEN flag set. An XMIS scan, short for Christmas, sends a packet with the FEN, URG, and PSH flags all set simultaneously like a Christmas tree with all the lights blinking, hence the whimsical name. And an NOL scan sends a packet with no flags set at all, which is also highly unusual. The core mechanism here relies on a specific behavior defined in CEHv13, which is the foundational document for PCP. The clever part, or the trick, is this. According to the RFC, if a port is open, compliant systems are supposed to receive these weird flag combinations and send no response at all. They should just drop the packet silently. However, if the port is closed, the target system is supposed to send back an RSTake packet. This is a critical distinction because it's the absence of a response that indicates an open port for these scan types, completely flipping the usual logic of looking for a positive response.
That's counterintuitive. But the source mentions a huge caveat. Windows OSs often ignore this RFC 793 standard in this specific regard, so these scans might not be effective against Windows targets, which is a pretty important limitation to remember, isn't it?
That's a key strategic limitation, absolutely. Microsoft Windows systems, historically and often currently, ignore this part of RFC 793 and might not respond as expected, regardless of whether the port is open or closed. They might just ignore the weird packet or sometimes send an RST regardless. So these techniques, FIN, XMIS, and ULL scans, are primarily effective against systems with BSD-derived TCP IP stacks, which includes many UNX-like operating systems, Linux, macOS, FreeBSD, etc. The Nmap commands are nmap-x target IP for XRIS scan, nmap-f target IP for FEN scan, and nmap-n target IP for NUL scan. Their main advantage is being highly stealthy, often slipping past firewalls and logging systems that are looking for the initial SYN packet of a connection attempt. But they do require raw socket access, meaning super user or administrator privileges, and you really need to have a good guess about the target OS for them to be reliable.
Okay, very interesting. OS-dependent stealth. What about a TCP MIMAN scan? How does that differ from these inverse TCP flag scans? It sounds similar but distinct.
A TCP Mammon scan, named after its discoverer, Uriel Mammon, is very similar in its intent to evade detection using unusual flag combinations, but it uses a specific FINEC probe packet. Again, it primarily exploits specific behaviors in BSD-derived systems. The critical difference in how it interprets the response is key. According to the original discovery, if the port is open, compliant BSD systems will typically silently drop the FINEC packet, meaning no response is received. If the port is closed, the target generates and sends back an RST packet. If the port is filtered by a firewall that blocks the probe, you might get an ICMP unreachable error message back. The Nmap command is nmap-sm target IP. The silently dropped packet for open ports is a key differentiator here, making it potentially quite stealthy by leaving no explicit trace for open ports on certain systems. But like the inverse scans, it's OS-dependent and less common now.
Right. An ACK flag probe scan takes yet another interesting approach by analyzing the header information within the RST packets that come back. What clever trick is this one playing? It sounds like deep packet analysis.
Yes, the ACK flag probe scam is quite ingenious, though perhaps less reliable on modern systems. It sends ACK probe packets, similar to the ACK ping for host discovery, but used here for port state. It then meticulously analyzes the time to live, or TTL value, and the TCP window size field in the RST packets that are received in response. The idea is to exploit subtle differences in how different OSs or even different port states might set these values in the RST packet they generate. In TTL-based analysis, the theory is that if the TTL value of the return RST packet is, say, significantly less than 64, which is a common initial TTL for Linux Unix systems, it might suggest the port is open, perhaps because the packet generation path is different for open versus closed ports on some stacks. The source gives an example. Maybe port 22 returns an RST with TTL 50, while other closed ports return RSTs with TTL 80, suggesting maybe Windows. This discrepancy implies port 22 is open, maybe on a different OS behind a firewall. The nmap command is nmap-tittle-time target.
That's a very subtle inference. Definitely depends on the specific stack. But what if all the TTL values are consistent across the RST responses you get back? Does that mean the scan failed?
Not necessarily. That's where window-based analysis comes in. If the TTL values are the same, you then look at the TCP window size field in those RST packets. On some older systems, if the window value of the RST packet returned for a particular port is non-zero, that port was considered open. Whereas closed ports might return an RST with a window size of 0. For instance, if port 22 RST has a window of 512 while others are 0, the inference was that port 22 is open. This is useful when TTL values are consistent or perhaps normalized by intermediate devices. The nmap command is nmap-sa stupby target IP. This ACK scan technique, nmap-sa target IP generally, can also be used just to check firewall filtering. If you send an ACK probe with a random sequence number and get no response, it likely means the port is filtered by a stateful firewall but didn't recognize an existing connection. If you do get an RST response, it means the packet got through, and the port is likely unfiltered, either open or closed. While these ACK scans can sometimes evade simpler IDS signatures, they're often extremely slow and primarily exploit behaviors in older OSs. They're niche but can be effective in specific older environments or for firewall rule testing.
Okay, very nuanced. Now here's one that sounds like it's straight out of a spy novel and perhaps the most ingenious in terms of pure stealth. The idolapid header scan, often called the zombie scan. This one sounds incredibly sneaky because the attacker never actually touches the target directly with their own IP address.
It is truly one of the most brilliant and conceptually complex scanning techniques ever devised. The IDLE scan is a completely blind scan. The attacker never sends a packet to the target from their own IP address. Instead, they cleverly leverage or impersonate another computer on the internet, a chosen zombie host, to perform the scan indirectly. The ingenious part is that it relies on exploiting the predictable behavior of the IP identification, or IPDD number in the IP header. Most operating systems increment this IPD number sequentially for every single packet they send out onto the network. The IDLE scan uses this predictable incrementing as a side channel. It works in 3 distinct rapid steps. Step 1. Find a suitable zombie and probe its IPD. The attacker first needs to find a truly idle machine on the internet, one not sending much traffic, that uses a predictable incremental IPD. They then probe this zombie to get its current IPD value. Let's say it's X. This is usually done by sending an unsolicited SYNAC packet to a port on the zombie. The zombie, not expecting this packet as part of a connection, responds with an RST packet, and that RST packet contains its current IPDX. Step 2. Attacker scans the target via the zombie. Now, the attacker sends a SYN packet to the actual target machine on the specific port they want to test. But crucially, they spoof the source IP address of this SYN packet to be the zombie's IP address. Now watch what happens. If the target port is open, the target machine receives the SYN, appearing to come from the zombie, and responds with the SYNEC packet back to the zombie. The zombie, again, receives this unexpected SYN, doesn't know what connection it belongs to, and sends an RST packet back to the target to kill the connection attempt. Critically, sending this RST increments the zombie's ITD to X+1 if the target port is closed. The target machine receives the SYN, appearing from the zombie, and responds with an RST packet directly back to the zombie. The zombie receives this RST packet, but since RSTs don't typically require a response, the zombie simply ignores it and does not send any packets. Its IPD remains X. Step 3. Attacker reprobes the zombie's IPD. The attacker quickly sends another SYNEC probe to the zombie, just like in Step 1. The zombie responds with another RST packet containing its new IPD. Now the attacker checks the value. If the new IP ID is X+2, this means the zombie sent 2 packets since the first probed the RST back to the attacker in Step 1, A and D the RST back to the target in Step 2. This only happens if the target port was open. If the new IP ID is only X+1, this means the zombie only sent 1 packet since the first probed the RST back to the attacker in Step 1. It did not send an RST to the target in Step 2. This only happens if the target port was closed.
Wow, that is incredibly clever. So you're essentially using a third-party, completely unaware zombie system as a proxy in a side channel to determine the target's port state. You never directly interact with the target using your real IP. For our listener, this highlights the sheer ingenuity attackers can employ for truly blind scanning and completely evading detection based on source IP logging. It turns a predictable OS behavior, IPID incrementing, into a powerful, stealthy information leak. The Nmap command looks complex too. Nmap-ppn-pisi, zombie IP, target IP.
It's definitely an advanced technique, and its effectiveness depends heavily on finding a suitable idle zombie host that increments its IPAD predictably and isn't behind a firewall that messes with the packets. But when the conditions are right, it's arguably the stealthiest TCP port scan possible because your IP never appears in the target's logs.
Amazing. Okay, we've covered a lot of sophisticated TCP scanning methods. What about UDP scan for port discovery, given its connectionless nature? How does that work, and what are its main challenges compared to TCP?
Right, UDP scan works quite differently because UDP is connectionless. There's no handshake to manipulate. The scanner simply sends UDP packets to the target ports being tested. Here's the challenge. If a UDP port is closed, the target host typically sends back an ICMP port unreachable message, type 3 code 3. This positively identifies the port as closed. However, if the port is open, UDP services often do not send any response at all. They just silently accept the data, or ignore it if it's malformed. This lack of response for open ports makes it incredibly challenging to distinguish between an open port and a filtered port, where, say, a firewall might just be silently dropping the UDP packet before it even reaches the application. In both cases, the scanner gets no reply. The Nmap command is nmap-u target IP.
Ah, okay, so this is like throwing that message in a bottle into the ocean again. If it washes back ashore, clearly marked no delivery, you know the port is definitely closed. But if it just disappears, the port might be open and silently accepting messages. Or the bottle just got lost in transit due to filtering. That ambiguity must make UDP scanning generally slower and less definitive than most TCP scans.
It absolutely does. That's the perfect analogy. UDP scanning is often much slower than TCP scanning, primarily due to ICMP error rate limiting implemented on many systems. Operating systems deliberately slow down the rate at which they send port unreachable messages to avoid being overwhelmed or used in amplification attacks. This forces the scanner to wait longer for potential replies or timeouts, and it usually requires privileged root admin access to read the raw ICMP error messages. However, it can sometimes be more effective or efficient on Windows-based systems, which historically tend to have less stringent ICMP rate limiting compared to some Unix systems, making UDP scans potentially faster against Windows targets. It's a necessary tool because many important services run over UDP, like DNS, DHCP, SNMP, some VPNs.
Right, you can't just ignore UDP.
Yeah.
Now, a lesser known but increasingly important transport layer protocol, especially in telecommunications and things like voice over IP, VoIP, is Stream Control Transmission Protocol, or SCTP. How does scanning work for that protocol, and why should ethical hackers be aware of it, even if it's less common than TCP UDP?
That's a great point. SCTP is a reliable, message-oriented alternative to TCP and UDP, designed for specialized applications, particularly in telecom signaling, like SS7 over IP, because it natively supports features like multi-homing, having multiple IP addresses per connection, and multi-streaming independent streams within one connection. It uses a more complex four-way handshake for establishing an association, its term for connection, involving cookie echo chunks, which is different from TCP's three-way handshake. Nmap supports two main types of SCTP scans. The SCTP IGI scan is conceptually similar to a TCP SYN scan. The attacker sends an INIT chunk, which is analogous to TCP's SYN packet. If the target port is open and listening for SCTP associations, the target sends back an INIT ACK chunk. If the port is inactive or closed, the target sends back an abort chunk. The Nmap command is nmap-cy target IP. This scan method clearly differentiates between open, closed, and filtered states. No response often means filtered, similar to how a TCP SYN scan works. It's the primary SCTP scan type.
Okay, so ISC scan is the SCTP equivalent of a SYN scan. What about the other SCTP scan mentioned, the SCTP cookie echo scan?
The SCTP cookie echo scan is a more advanced and potentially stealthier technique specific to SCTP. The attacker sends a specially crafted cookie echo chunk to the target port. According to SCTP standards, if the port is open, the packets containing just a cookie echo chunk should typically be silently dropped by the endpoint, meaning no response is received by the scanner. If the port is closed, the target sends back an abort chunk. The Nmap command is nmap-sz target IP. Its potential advantage is being less conspicuous than an INIT scan because open ports don't respond. However, a significant disadvantage is that it cannot clearly differentiate between open ports and filtered ports, since both result in no response. Nmap often reports these as open filtered, adding to the ambiguity similar to UDP scans. For our listener, while SCTP might seem niche, being aware of it and how to scan for it is increasingly important as these protocols become more prevalent in specialized infrastructure like 5G networks and critical communication systems.
Good point. Got to keep up with the protocols. Now, beyond the main transport protocols, there are other services or methods to look for, like those enabled by Universal Plug-and-Play or UPnP. This brings us to SSDP scanning and also the LISA scan. What kind of intelligence can these provide?
Right. Simple Service Discovery Protocol, SSDP, is a network protocol based on the IP suite that allows network devices to discover each other's presence and capabilities. It's the foundation for Universal Plug-and-Play, UPnP, which allows devices like printers, routers, and media servers to easily connect and communicate on a network, often automatically configuring things like port forwarding. Attackers can perform SSDP scanning, usually via multicast messages on UDP port 1900, to detect devices running UPnP services. Why? Because UPnP has historically had numerous security vulnerabilities, including buffer overflows and configuration flaws that could allow remote code execution or be exploited for denial of service amplification attacks like reflection attacks. So finding UPnP is often finding potential weakness. The list scan, on the other hand, nmap-SL target IP range, is a much more passive, indirect host discovery method. It doesn't actually send any packets to the target hosts. Instead, it simply generates and prints a list of the IP addresses and, importantly, any associated host names for the specified target range. By default, it performs reverse DNS lookups on the target IPs to get those names. It's useful as a preliminary sanity check to see what IPs are supposed to be in a range according to DNS without alerting the targets. It can also sometimes help detect incorrectly defined IP addresses or misconfigured DNS records. It's purely reconnaissance, no active probing.
Okay. We've mostly talked about IPv4 scanning, the addresses we're all familiar with. But what about the next generation of IP addresses, IPv6? That's a whole new ballgame for scanning, isn't it? The sheer scale of the address space sounds completely daunting.
It absolutely is a different ballgame. IPv6's massive address space, 128 bits compared to IPv4's 32 bits, means a single typical IPv6 subnet, 64, has 264 possible host addresses. That's 18 quintillion addresses. This makes traditional linear scanning, where you try every possible address in sequence, completely computationally infeasible. The source notes that a comprehensive scan of a single 64 subnet could literally take 5 billion years with current technology. It's just not practical.
5 billion years. Okay, so attackers can't just scan everything. How do they approach IPv6 host discovery and scanning then?
They have to shift their strategy dramatically. Instead of brute force scanning, they often need to harvest specific IPv6 addresses first. They might find these from listening to network traffic, neighbor discovery protocols, analyzing logs, scraping websites or emails, exploiting DNS records, or looking for predictable patterns in how organizations assign addresses. Once they have a list of potential target IPv6 addresses, they can then use tools like Nmap, which fully supports IPv6 scanning using the 9-6 option, Nmap 9-6 target IPv6 address or domain. The scanning techniques themselves, SYN scan, UDP scan, etc., work similarly, just over IPv6.
So for you, our listener, the key takeaway for IPv6 scanning is that while scanning an entire subnet is impractical, the game shifts entirely to targeted reconnaissance and harvesting initial addresses. Once an attacker compromises one IPv6 host, they might then be able to probe specific multicast addresses, like the all-hosts address FS02.1, to find neighbors, or look for sequential or algorithmically generated address schemes within a known organizational range. It's much more about finding the needle in an unimaginably large haystack rather than scanning the entire haystack.
Precisely. It fundamentally shifts the focus from brute force scanning, which is dead in IPv6, to more targeted reconnaissance, intelligence gathering, and exploiting initial footholds to discover more hosts. A very different challenge.
Right. Now, just like with host discovery, AI is proving to be a truly powerful assistant for port and service discovery as well, making these complex tasks and command constructions more approachable, especially for less experienced users.
Indeed, AI can now generate highly specific Nmap commands for various port scans, significantly streamlining the process and helping users leverage Nmap's full power without needing to be an expert in its syntax. For example, a simple prompt like, use Nmap to find open ports on target IP 10.n of that 1.1 mine would likely generate a standard Nmap command, maybe Nmap 10.10.1.1 on. Or if you want more stealth, prompting perform stealth scan on target IP 10.n.1 alum and cited the results would probably give you Nmap ven-ss10.1.on.11. Even for those more obscure scans, asking perform an XMAS scan on target IP 10.10.1.11 would directly generate the correct command. Nmap -x 10.1.1.11. It handles the basics easily.
Okay, those are straightforward mappings. But what about something more complex, like pulling very specific information from a scan of multiple IPs, maybe from our host discovery file, and structuring the output just right for further analysis and reporting? That's where AI truly shines, I imagine, in handling the complexity.
AI can absolutely handle that level of complexity. Imagine giving it a prompt like this. Use Nmap to scan for open ports and services against a list of IP addresses found in the file scan1.txt. Copy only the port number, protocol, service name, and version information, along with the respective IP address, to a new file called scan3.txt. That's a complex request. The AI would likely craft a powerful multi-stage command, potentially involving pipes and text processing tools, maybe something like nmap-sv digil scan1.txt open awk, nmap scan report for m.9 plus mnt at bay, $1, $3 and friend, scan-theta.txt. This command uses nfsv for version detection, ml scan1.txt to read the input list, open to only show open ports. Then it pipes the output to awk. The awk script here cleverly extracts the IP address when it sees a Nmap scan report line, and then for lines starting with a port number and protocol, it prints the captured IP, the port protocol, $1, the service name, $3, and concatenates the rest of the line, which usually contains the version info, $4 onwards. Finally, scan3.txt redirects this precisely formatted output. This level of parsing and automation is a huge time saver compared to doing it manually.
Wow, yeah, that awk part alone would take some figuring out. And can AI also help with other tools in the ethical hacker's arsenal, like Metasploit, which has its own completely different command syntax and structure?
Absolutely. AI's ability to understand and generate commands for multiple tools based on natural language requests is incredibly valuable. For instance, if you prompt, use Metasploit to discover open ports on the IP address 10.10.1.22, the AI could generate the specific Metasploit command sequence, emissive console mash2qx, use auxiliary scanner port scanacp, set rosts 10.10.1.22, run, exit. This command launches the Metasploit console, MSF console in quiet mode Q, executes a series of commands /x, use auxiliary scanner port scanasp, loads the TCP port scanner module, set rosts 10.10.1.22, sets the target IP, run executes the scan, and exit closes Metasploit. It's a fantastic example of AI lowering the barrier to entry for complex frameworks and quickly executing multi-step operations based on a simple request.
That really is powerful. For our listener, this highlights the immense efficiency and learning potential of using AI. It can help craft precise commands, automate complex multi-tool workflows, and even help you understand how the commands work. It's truly a game changer for ethical hackers, freeing them up for deeper analysis rather than tedious command line construction and debugging.
Couldn't agree more. It accelerates the whole process.
Okay, so once you know a port is open, and you even know maybe what service is running on it, that's great intelligence. But knowing what specific version of that service is running on it, that's the next critical level of intel, isn't it? This is where you can potentially go from generic knowledge to finding a specific targeted vulnerability.
It's absolutely critically important because it's the direct link to known vulnerabilities. Every piece of software, every service, has a version number. And many specific versions have known, publicly documented vulnerabilities. Identifying the exact version allows an attacker or an ethical hacker doing vulnerability assessment to pinpoint specific exploits that might work against that exact version, drastically increasing the probability of a successful attack or finding a verifiable risk. It's like knowing a building has a specific brand and model of door, and then checking a database and finding out that specific model is known to have a faulty lock mechanism that can be easily bypassed. It turns general scanning into targeted analysis. Nmap performs this version detection primarily by examining the banners or responses from TCP and UDP ports. It uses its extensive Nmap service probes database, which contains thousands of probes and expected response patterns, to query services and accurately match their responses to known service and version signatures. It's essentially having a pre-built library of how thousands of different services talk and identify themselves. The Nmap command for this is simply nmap-sv target IP.
Right, NashSV for service version. And of course, AI can even help you craft these highly specific version detection scans, maybe combining multiple requirements into one elegant command.
Indeed. You could prompt something quite detailed like, use Nmap to scan all open ports on target IP 10.0.1.1, identify the services running with their versions, get the MASI address details, use a TCP Connect scan for reliability, be verbose, and tell me why Nmap thinks a port is open. The AI would likely generate a command like this: nmap-sv reason-vsd-epin 10.10.1.11. Let's unpack that. -sv enables service version detection. Reason displays the reason Nmap determined the port state. AG, SYNAC, def, no response, which is fantastic for understanding Nmap's logic and troubleshooting. -v increases verbosity for more detailed output during the scan. -t performs a TCP Connect scan, reliable but noisy. SFP tells Nmap to scan all 605.35 TCP ports. Open tells Nmap to only display results for ports it found to be open. And finally, the target IP. It's about getting comprehensive details and understanding the scanner's reasoning clearly.
Okay, that reason flag sounds particularly useful for learning. Now, these sophisticated scans, especially version detection or scanning all ports, can be incredibly time-consuming, particularly on large, complex networks or slow links. So for ethical hacker working under time constraints or trying to remain stealthy, how do you make these scans faster and more efficient without sacrificing too much accuracy? What are some key Nmap scan time reduction techniques that are crucial for real-world engagements?
That's a crucial strategic question for any real-world scenario where time is often limited, network resources might be constrained, or you need to minimize your footprint. The source offers several practical tips, all centered around smart resource management and focusing your efforts intelligently. First, and perhaps most importantly, omit non-critical tests. Don't run an intense, all-encompassing scan if you only need minimal information for your current objective. For instance, drastically limit the port ranges you scan. Do you really need to scan all 65,535 ports, or just the top 1,000, or maybe even just specific ports of interest? Or skip the port scan entirely, NISN, if you just need host discovery. Critically, avoid computationally expensive or time-consuming advanced scan types like script scanning, data.sc or script, service version detection, data.sv, OS detection, traceroute, or the aggressive options bundle A when they're not essential for your immediate goal. And always consider turning off reverse DNS resolution day when you don't strictly need host names, as DNS lookups can add significant overhead and delay, especially for unresponsive IPs.
Okay, so it's really about being strategically precise and surgical with what you ask Nmap to do, tailoring the scan to the specific information needed, and not just letting it run wild with default settings. Makes sense.
Exactly. Be intentional. Second, optimize timing parameters. Nmap provides the incredibly useful NashT option for timing templates, ranging from T0, paranoid, extremely slow, designed to evade ancient IDS by minimizing traffic, to T5, insane, very fast, potentially overwhelming networks, or getting less accurate results. This allows you to precisely control the aggressiveness and speed of the scan. You might need to slow down significantly, T0, T2, to avoid detection on highly monitored or sensitive networks, or you might be able to speed up dramatically, T4, T5, on trusted internal networks, or during less sensitive phases where speed is paramount. It's a direct trade-off between stealth reliability and speed. T3 is the default and often a good balance.
Right, tuning the speed. And UDP scans have different performance characteristics, right? They're often inherently slower due to that ICMP rate limiting we discussed.
They do. So third, separate and optimize UDP scans. UDP scans often have different performance requirements and are more affected by ICMP error rate limiting compared to TCP scans. Trying to scan TCP and UDP ports together in one Nmap run can sometimes be inefficient. It might be faster overall to run TCP scans first and then run a separate, perhaps slower timed NATHT2 or NATHT3 UDP scan focused only on relevant UDP ports. Fourth, upgrade Nmap. This might sound obvious, but newer versions of Nmap frequently include critical bug fixes, significant algorithmic enhancements for speed and accuracy, and better performance features, especially for things like local network ARP scanning, which is much faster now. Always try to stay updated with the latest stable release.
Good advice for larger networks. Just running one massive Nmap scan across everything can be a real drag on both time and potentially network resources, too.
That leads directly to the fifth point. Execute concurrent Nmap instances. If you have a large network block to scan, you can strategically divide it into smaller, manageable chunks or subnets and run multiple Nmap instances simultaneously, perhaps from different scanning machines or just different terminals targeting different ranges. This parallel processing significantly improves the overall time to scan the entire network. Sixth, scan from a favorable network location. This is crucial for context. If you're testing internal network security, defense, and depth, scanning from within the local network offers crucial insights into what an insider threat or a compromised system could see and reach. But if you're testing perimeter defenses, firewalls, IDICs, you absolutely must scan from an external location, realistically simulating an attacker's viewpoint from the public internet. The results will be vastly different. Finally, seventh, increase available bandwidth and CPU time. This is somewhat self-explanatory. More network bandwidth and a faster CPU on the scanning machine generally mean faster scans. Nmap has its own sophisticated congestion control algorithms built in to try and prevent network flooding and adapt to network conditions. But having ample resources helps. You can test its bandwidth usage and see if it's being limited by running it in verbose mode, BAFV or AFVV.
Okay, those are some really practical, actionable tips. For our listener, these techniques are truly crucial for making your scanning efforts efficient and effective in real-world scenarios, whether you're on the offensive security side performing a penetration test or on the defensive side doing vulnerability assessments. It's about strategy and efficiency as much as it is about the tools themselves.
Couldn't agree more. Smart scanning is efficient scanning.
All right, so knowing the service is running on a system is great. Knowing the version is even better, but knowing the underlying operating system, that's like knowing the very core identity of your target. This is where OS discovery, also called banner grabbing, or more accurately OS fingerprinting, comes in, and it's a critical piece of intelligence for tailoring attacks.
This is a profoundly important step, arguably one of the most valuable pieces of information you can gather during scanning. Why? Because it dictates so much of the subsequent attack strategy or defensive hardening approach. An attacker has a much, much higher probability of success if they know the target OS. Many vulnerabilities, exploits, configuration settings, and default credentials are OS-specific. Knowing whether you're dealing with a Windows Server 2019, an Ubuntu Linux 22.04 box, a specific version of FreeBSD, an older Solaris system, or maybe a Cisco iOS router completely changes the playbook. Different OSs have different default configurations, different patch cycles, different common weaknesses, and different available exploits. It narrows the focus immensely.
Okay, so how do scanners like Nmap figure this out? There are two main types of banner grabbing or fingerprinting mentioned. Active and passive. Let's start with active banner grabbing. What's Nmap doing under the hood here? Is it just asking, what OS are you?
Ha! If only it were that simple. No, active OS fingerprinting involves Nmap sending a series of carefully, specially crafted packets to the remote OS and then meticulously analyzing the unique nuances in its responses. This works because different vendors, and even different versions from the same vendor, implement the TCP/IP network stack in slightly different ways. These subtle implementation differences lead to unique response patterns or fingerprints. Nmap, for instance, employs a sophisticated series of about 9 core tests and many subtests specifically designed to elicit these differences and determine an OS fingerprint. These tests involve sending TCP packets with various unusual flag combinations like Synesy-Eneco, null, finchirk, sending probes to both open and closed TCP ports, sending UDP packets to likely closed UDP ports, and analyzing things like TCP initial sequence number, ISN predictability, IP identification, IP number sequencing, and TCP timestamp options. The goal is to find subtle but consistent patterns in how the target OS generates these values. We try to categorize these responses. Some older UNIAC systems use a traditional 64K increment for IPD. Others, like Solaris or FreeBSD, use random increments. Modern Linux often uses true random ISNs, and Windows frequently uses time-dependent increments for things like TCP timestamps. Nmap compares the collected responses against its extensive database, Nmap OSDB of known OS fingerprints. The Nmap command for this active probing is simply nmap-acho target IP.
Okay, so it's actively poking the system with a battery of highly specific, sometimes weird questions or probes, and observing its unique accent, or quirks, in its responses to infer its identity based on a known database of accents. Now, what about passive banner grabbing or passive OS fingerprinting? This sounds incredibly stealthy, as the name implies, because it doesn't involve any direct interaction or sending probes to the target.
Indeed, passive OS fingerprinting is incredibly stealthy because it doesn't involve sending any active probes or packets directly to the target system you're trying to identify. Instead, it works by capturing and analyzing existing network traffic that originates from the target, essentially sniffing the packets passively as they traverse the network to find subtle, telltale signs of the OS that generated them. These signs can come from various sources. Sometimes error messages generated by services running on the target might inadvertently reveal the server type or underlying OS. Or you might get clues from direct analysis of the headers in sniffed network traffic. Even subtle hints in higher-level protocols, like specific HTTP server headers or page extensions in URLs, like ASPX, often indicating a Microsoft ISA server and thus a Windows platform, or PHP perhaps hinting at a Linux backend with Apache or Nginx, can contribute.
That's fascinating, relying purely on observation. What specific low-level packet header parameters are ethical hackers or passive tools looking at for this kind of fingerprinting? This sounds like real digital detective work examining clues left behind.
The source identifies 4 key packet header parameters that are often valuable for passive OS fingerprinting. First, the time to live TTL field in the IP header of outgoing packets. Different OSs typically set different initial TTL values when they create a packet. The example, Linux Unix often start at 54, Windows families often start at 128, Cisco routers often use 255. By observing the TTL value in a captured packet at the sniffing point and maybe estimating the number of router hops it is likely traversed, you can often deduce the original starting TTL and thus make a good guess about the originating OS. Second, the default TCP window size advertised by the OS and TCP packets. AG Linux might use 5840 or similar. Modern Windows often uses 65535 or scales it. FreeBSD might use 65535. These defaults can be characteristic. Third, whether the DF don't fragment bit in the IP header is set. Most modern operating systems set this bit by default, but some older or niche OSs like SCO or older OpenBSD versions traditionally did not set it. And fourth, the TOS type of service field in the IP header, although this is often less reliable as an OS indicator as it's frequently set to 0 or modified by applications or network devices based on traffic type rather than being a fixed OS characteristic. TTL and window size are usually the most useful passive indicators.
Okay, so you could, for instance, sniff a packet coming from a target server. You see its TTL is, say, 45, which if it crossed maybe 19 routers would suggest an initial TTL of 64 pointing towards Linux Unix. You see its TCP window size is 0 by 7078, which is 321 Creo in decimal, a known Linux default from older kernels. You see the DF bit is set and the TOS is 0x0. And based on comparing that combination with a database of known passive signatures, you could potentially quite confidently point to a Linux kernel, maybe around the 2.2.x era based on that window size. It's like finding a series of unique, subtle clues that, when combined, paint a fairly clear picture.
Precisely. The TTL, after accounting for estimated hops back to the source, can strongly suggest the initial value. The window size can be a very good indicator, especially if it matches known defaults. By combining these observations from passively captured packets, you can often infer the OS with a strong degree of confidence without ever alerting the target system itself. For our listener, passive fingerprinting is incredibly valuable because it's so stealthy. It doesn't leave any active scanning traces on the target system that an IDS or diligent sysadmin might flag. It's excellent for silently identifying the OS of web servers, proxy firewalls, or potentially rogue systems on a network just by observing the traffic they naturally generate.
Very cool. Now, one of the most powerful tools for actually performing this passive analysis is Wireshark, the ubiquitous network protocol analyzer, the packet sniffing tool par excellence. How would you practically use Wireshark to infer an OS passively?
Using Wireshark is a direct, hands-on way to perform this passive OS inference without sending a single probe yourself. You simply start a capture on a network segment where traffic from your target system is flowing. Then, you filter for traffic originating from the target's IP address. You'd typically look at the very first TCP packet in a new session initiated by the target, like the SYN or ScienceSig packet. You'd expand the IP header details in Wireshark's packet details pane and look specifically at the displayed TTL value and the TCP window size value. By comparing these observed values to a known table or database of OS-specific defaults, for example, a TTL close to 128 often indicates Windows, While a TTL close to 64 often indicates Linux Unix, you can make a highly educated guess about the target OS. Seeing a window size that matches a known default for a particular OS further strengthens the inference. This is powerful because you're not sending any probes, you're just observing existing communications flowing past your sniffing point.
Okay, practical application there. Now, Nmap isn't just for basic scans or core OS detection. It has that powerful scripting engine we mentioned earlier. How does the Nmap script engine and SE contribute to OS discovery, maybe getting more detail? And what about IPv6 fingerprinting specifically? How does Nmap handle OS detection in the IPv6 world, especially given the challenges of that vast address space we talked about?
Right, the Nmap scripting engine, NSE, is incredibly versatile and extends Nmap's capabilities far beyond the built-in scan types. NSE allows users and the Nmap developers to write and share scripts written in the Lua language to automate a huge variety of networking tasks, including more refined or specialized OS discovery techniques. For example, the source mentions the Semios discovery script. If Nmap finds SMB ports open, common in Windows environments, this script can query the SMB service for detailed OS version information, hostname, domain name, and sometimes even the exact build number, often providing much more granularity than the standard EVO fingerprinting. You can run default scripts, many of which aid discovery, alongside OS detection using nmap-osc target IP, where NIC is equivalent to script default, or specify custom scripts with script name. NSE adds layers of intelligence on top of the core scans. For IPv6 fingerprinting, Nmap uses a similar active probing approach as it does for IPv4, but it leverages probes and analyses specifically designed for IPv6 protocols and behaviors. Given the massive address space, just finding the target is the first challenge, but once found, Nmap's IPv6 OS detection engine is quite sophisticated. It sends nearly 18 specific probes tailored for IPv6, including analyzing IPv6 sequence generation patterns, using ICMPv6 echo requests, leveraging the IPv6 node information query protocol it supported, and performing various TCP and UDP specific tests over IPv6. It then compares the responses to its dedicated IPv6 OS fingerprint database. You simply combine the IPv6 option manically 6 with the OS detection option nmap level 6 NASHO target IPv6 address. It's about adapting the proven active fingerprinting methodology to the nuances and protocols of the IPv6 world.
Okay, so Nmap is equipped for both IPv4 and IPv6 OS detection. And of course, bringing us back to our recurring theme, AI is right there, ready to help automate OS discovery as well, simplifying the command construction for these sometimes complex tasks.
Absolutely. AI, like ChatGPT or similar models, can generate precise commands for various OS discovery methods, making the inference process quicker and more accessible, especially if you're trying to combine different techniques. For instance, you could prompt something simple like, use TTL to identify the operating system running on the target IP address 10.10.1.101. The AI might suggest a command leveraging the basic ping tool, maybe like this. Ping -C1 10 byte 1 on, and it goes check the TTL value from the response to infer the OS Linux Unix 64 Windows 128. This sends just the single ICMP echo request -C1, and then if successful provides clear instructions via echo on how to interpret the TTL value from the response, leveraging that common OS characteristic we discussed.
Simple but effective for a quick check. Or maybe for a more focused output, they cut straight to the relevant TTL detail without the extra echo text.
Sure, you could ask. Use TTL to identify the operating system running on the target IP address 10.0.1.9. This might give you a slightly more refined command like ping -C1 10.10.1.9 grep. The pipe sends the ping output to grep, which then filters and displays only the line containing a little, making it easier to spot the key value without having to parse the full response. AI can even help orchestrate NSE scripts for OS discovery, if you prompt. Use Nmap script engine to perform OS discovery on the target IP addresses listed in the file scan.txt and save the results. The AI could generate something like nmap -il scan1.txt audio script default script args new targets -on os discover results.txt. This command tells nmap to read targets from the input list -il, perform standard OS detection audio o, run the default set of NSE scripts script default, many of which gather OS related info, possibly use script arguments like new targets depending on the script, and save the combined normal output onto a file named os discover results.txt.
That's really useful. For our listener, this again shows how AI significantly simplifies the execution of these nuanced OS detection commands and workflows. It makes it easier to infer critical OS information quickly and efficiently, even leveraging Nmap's powerful but sometimes complex scripting engine, lowering the technical barrier.
It really does make advanced techniques more accessible.
Okay. Now, we've talked a lot about gathering information, but what about the defenses? Intrusion detection systems, IDS, and firewalls are supposed to be our digital bouncers, meticulously guarding the network perimeter and maybe even internal segments, looking for exactly this kind of scanning activity. But ethical hackers and adversaries need to know how attackers try to sneak past them. Understanding evasion is just as important as understanding scanning because it helps build better, more resilient defenses.
It's a constant high-stakes cat-and-mouse game, absolutely. IDS and firewalls, despite their increasing sophistication, inherently have limitations, performance trade-offs, reliance on known signatures, potential misconfigurations, and attackers are constantly actively probing and exploiting these limitations. This next section is all about evasion techniques, the methods used to craft and send those intended packets, the scam probes, to a target in such a way that they evade or bypass these security mechanisms, effectively sneaking past those digital bouncers without tripping an alarm or getting blocked. Knowing these techniques as a defender is absolutely critical for tuning your own systems and building truly robust, layered security that anticipates these tricks.
Right, so let's look at some of these key IDS and firewall evasion techniques. The core idea seems to be manipulating the packets or the scanning process itself to fly under the radar. Let's start with packet fragmentation. This sounds like trying to sneak a message through by sending it in tiny, separate pieces.
Exactly, that's the core concept. Packet fragmentation involves deliberately splitting a single probe packet, like a TCP SYM packet or UDP probe, into several much smaller IP fragments before sending them across the network. The ingenious idea here is that IDS and firewalls often have to capture and queue all the fragments of a packet before they can reassemble the original packet and inspect its full contents, like the TCP header and flags. This reassembly process consumes significant CPU and memory resources on the security device. To avoid becoming a performance bottleneck, many older or less aggressively configured IDS firewalls are simply configured to skip inspection of fragmented packets altogether, or perhaps only inspect the very first fragment, which might not contain the crucial TCP header information if the attacker fragments cleverly. Attackers leverage tools like Nmap, using the Moire flag or A for even smaller fragments, or HBing3, to deliberately fragment their scan packets. When the TCP header itself is split across multiple fragments, it can effectively evade packet filters or IDS rules that are looking for specific flag combinations or patterns within a single contiguous header. In some cases, if the target system has trouble reassembling the fragments correctly, it could even lead to system instability, crashes, or monitoring dumps, making fragmentation a potentially disruptive technique as well as an evasive one.
So it's like sending that book through the mail again, but ripping out every single page and sending each page in a separate envelope. The post office or the firewall ADS might just give up trying to reassemble the whole book for performance reasons, especially if they have a huge volume of mail to process. This exploits a fundamental performance versus security trade-off inherent in many defensive systems.
Precisely. It's a classic example of exploiting a system's need for speed and efficiency against its security posture. It forces the defender to choose: inspect everything slowly, or let some potentially malicious fragment slip through for the sake of performance. Another interesting, though perhaps less common now, technique is SORC routing. This is where the attacker doesn't just send a packet and let the internet routers decide the path. Instead, the attacker tries to specify the exact path, a list of specific router IP addresses that a packet should take through the network to reach the target. They attempt to manipulate the IP options field within the IP datagram header to define either a loose source route, must hit these routers but can take other hops in between, or a strict source route, must take only this exact path. The goal is to bypass specific firewall or IDS configured routers that might otherwise inspect or block the traffic if it followed the normal route.
So instead of letting the network's GPS decide the fastest or standard route, you manually plot a specific course on the map, deliberately navigating around known traffic cameras, firewalls, or heavily monitored intersections, IDS choke points. It aims to circumvent the standard routing decisions that a firewall's security policy might be relying on.
That's a good analogy. It tries to bypass the routing logic that firewalls often integrate with their security policies. However, most routers on the internet today are configured to ignore or drop packets with source routing options enabled due to security concerns. So its practical effectiveness is limited on the public internet, though it might still work in some internal network scenarios.
Okay, less common now. How about source port manipulation? This involves changing the attacker's port number.
Yes. Source port manipulation is a common and often effective trick. This involves the attacker changing their actual source port number for the outgoing scan packets to a well-known or commonly trusted port number. Think ports like 80 HTTP, 53 DNS, 25 SMTP, or sometimes even 20 FTP data. The strategic advantage here is that firewalls, especially simpler packet filters or even stateful firewalls looking at outgoing traffic, are almost universally configured to trust and allow traffic originating from these common, essential service ports, assuming it's legitimate outgoing traffic initiated from an internal server or client. By making their scan packets look like they're coming from port 80, the attacker hopes the firewall will let them pass through outbound filters or perhaps apply less scrutiny. The Nmap command is nmap-g port number target IP, or the more explicit source port number.
Right. It's like that delivery person trying to get into a secure building again. If they show up in a generic uniform, their real random high source port, they might get stopped and questioned at the gate, the firewall. But if they cleverly put on a uniform for the pizza delivery guy, making their source port 80 or 53, the gate guard might just wave them right through without a second glance, assuming they belong. It exploits an implicit trust, often placed on traffic from standard service ports.
Precisely. It plays on the common firewall rule assumptions. Next, we have IP address decoy. This technique is about hiding in a crowd. It involves generating or manually specifying multiple fake source IP addresses, known as decoys, alongside the attacker's real scanning IP address when sending probes. It makes it appear to the target system and its logging mechanisms that multiple disparate systems are scanning it simultaneously. This effectively obscures the actual attacker's IP address within the flood of logs generated by the decoys, making forensic analysis and attribution much harder. It's a smokescreen. Nmap provides two convenient options for this. Nmap-e rnd.10. Target IP generates a specified number, 10 in this case, of random decoy IPs and randomly places your real IP among them in the scan packets. Or you can manually specify a list of decoys and control your position. Nmap-d decoy1, decoy2 me, decoy3, target IP, where me explicitly indicates the position where Nmap should insert your real IP address within the list of decoys sent in the packet.
So imagine that crowd of people all knocking on a door at the same time again. The person inside hears dozens of knocks, and their security camera log is filled with images of different faces, the decoy IPs. They can't easily tell who the real instigator, the attacker's true IP, because it's lost in all the noise. This sounds very effective for blurring your tracks in the target's logs.
That's exactly the effect it aims for, hiding in plain sight amidst controlled noise. The main drawbacks are that using decoys can significantly slow down the scan due to the increased number of packets being sent and potentially waited for. Also, it's not always completely foolproof if the target network employs sophisticated defenses like router path tracing, which might reveal the real source path despite decoys, or response dropping mechanisms that try to identify which source IPs are actually eliciting valid responses. But it definitely makes simple log analysis much harder.
Okay, how about IP address spoofing itself? This seems like the ultimate in misdirection, pretending to be someone else entirely. How is it used in scanning evasion?
IP address spoofing is indeed about changing the source IP address in the packet headers to make the attack appear to come from someone else entirely, perhaps a trusted internal host within the target network, another unrelated external system, or even a completely non-existent host IP address. Since firewalls often filter traffic based on source IP addresses, example, denying traffic from known bad IPs or allowing traffic from trusted internal IPs, by spoofing a trusted or permitted IP, the attacker attempts to bypass these firewall rules directly. A key point, especially regarding scanning. If the attacker spoofs their source IP, they generally cannot receive the replies to their scan probes because the target sends the replies back to the spoofed address, not the attacker's real address. This means spoofing is primarily useful for blind scanning techniques where you don't need a direct reply, like maybe trying to trigger a side effect or using a different channel like the ideal scan zombie, or for certain types of denial of service attacks. For example, if you spoof a non-existent source address in a SYN flood, the target replies to that non-existent address and uselessly waits for a timeout, consuming its own connection table resources. CEHv13 is often used for crafting packets with spoofed source IPs. CEHv13 www.certifiedhacker.com, Critico ANIS 7.7.7, where ANIS specifies the desired spoofed source address 7.7.7.7 in this case. But remember, for most standard scanning techniques that rely on receiving replies like SYN scan, Connect scan, UDP scan, simple IP spoofing prevents you from getting the results directly.
Right, so spoofing is more for blind attacks or hiding the source of DOS, not typically for interactive scanning where you need the answers back. Makes sense. It's like sending a letter with a fake return address. You can cause trouble, but you won't get any mail back.
Exactly. And finally, operating at an even lower level of the network stack, layer 2, we have MAC address spoofing. How does changing your hardware address help evade firewalls or IDS? Yes, MACAS's address spoofing involves changing the media access control AC address associated with the attacker's network interface card, NIC, to that of a different, perhaps legitimate user or device already present on the local network segment. This is primarily effective within a local network context. Why? Because network access controls, like port security on switches, and some internal firewalls or wireless access points often filter traffic based on MAC addresses, allowing only specific pre-approved MS addresses to communicate or access certain network resources. By spoofing the M address of an already authorized device, attackers can potentially bypass these Layer 2 security controls and masquerade as a legitimate user, gaining unauthorized access to the network segment or specific resources. It's particularly useful for bypassing NAC, network access control, or getting onto restricted Wi-Fi networks if mass filtering is used. Nmap allows you to do this during scans using options like Nmap-SSTEP SpoofMac 0 target IP, which uses a completely random Minhu address. Or you can make it look slightly more legitimate. Nmap-ST-SpoofMac vendor target IP, which generates a random many address but ensures the first 3 bytes, the OUI organizationally unique identifier, match those of a specified vendor like Apple, Cisco, or Dell, potentially making the spoofed address look less suspicious in logs.
Ah, okay. So empty spoofing is more about bypassing local network access controls rather than perimeter firewalls. It's like changing the license plate on your car to match that of a resident in a private gated community to get past the security guard at the gate.
Exactly. It's a Layer 2 evasion technique.
Wow. These techniques truly reveal that network security is never absolute. It's a dynamic interplay between attack and defense. Understanding these evasion tactics isn't just for attackers. It's absolutely essential for you as a defender to build more robust, layered, and resilient defenses that can anticipate and ideally detect or mitigate these clever tricks. You need to know how they try to hide to know how to find them. Now, to bring it all together, remember how AI can help automate these complex multi-stage tasks, even creating entire scripts for you, making these sophisticated scanning and evasion workflows even more accessible and potentially dangerous.
This is where AI truly becomes a force multiplier for both ethical hackers and malicious actors. The ability to combine host discovery, various port scanning techniques, version detection, OS fingerprinting, and even some basic evasion tactics into a single automated script generated from a natural language prompt is incredibly powerful. You can now essentially prompt an AI. Develop a script that will automate my initial network scanning efforts. It should find live systems in the 10.10.0.1.024 range. Then for those live systems, find open ports, identify running services and their versions, attempt OS detection, run default NSE scripts, use a reasonably stealthy scan timing, and save all the results.
And what would such a script, generated by AI perhaps, look like in practice? Combining all these elements we've discussed,
The AI could generate a bash script, maybe similar to this example provided in the source, which integrates multiple Nmap functionalities into a logical workflow. Bash, #binbash, #simple automated scanning script, target range, 10.vin.1.024, live hosts file, livehost.txt, scan results prefix, scan results, echo, starting comprehensive network scan on target range, echo, live hosts found and saved to echo, live hosts found and saved to echo, echo, live hosts found and saved to echo, echo, failed to discover live host, exit 1, echo, echo, plus displaying Nmap scan results, echo, plus displaying Nmap scan results, echo, plus network scan complete.
Okay, let's quickly break down what that script is doing because it nicely combines so many of the concepts and commands we've discussed into an automated sequence.
Sure, first, after setting some variables for clarity and printing a start message, the core logic begins. Nmap daesys omitrange dogretrange og awk upprint $2 performs that fast ping scan -7s on the target range to discover only live hosts. It outputs the results in grippable format, OG pipes, that output to awk to specifically extract just the IP addresses of up hosts and saves them to the file specified by let's host file. The NS ensures the next command, like printing the file contents, only runs if the host discovery is successful. That provides basic error handling if it fails.
Right, so step 1 is efficient host discovery, and the second, more comprehensive Nmap command in step 2.
Nmap ham.if host file nym ssSVO script default honesty 3 reason SOA scan results prefix, then takes that list of live hosts, my host really fast, and performs a series of scans against only those active IPs NSS Stealthy SYN scan for port discovery, NSS service version detection, Anajo operating system detection, script default, runs the default set of Nmap scripting engine scripts for even more information gathering. T3 sets a normal timing template, a balance between speed and stealth. Reason displays the reason Nmap determined each port state. Chan results prefix saves the comprehensive results in all Nmap formats, normal.nmap, XML.xml, and grippable.gmap to files prefixed with the value of scan results prefix. Again, NNN handle basic success failure flow.
Got it. Combining multiple scan types efficiently against only the live hosts. And finally, step 3 just cats the results.
Exactly. That last command, cat scan results prefix.map, simply displays the normal human-readable Nmap scan results file directly to the console, so the user running the script can immediately see the key findings without having to open the file separately. This whole script demonstrates the ultimate goal for efficiency. Automating the entire initial information gathering workflow, find live hosts, then deeply scan only those hosts, allowing the ethical hacker to become highly efficient in both attacking, finding vulnerabilities, and defending networks, identifying weaknesses. AI's ability to help generate and refine such scripts is, as we said, not just a tool, it's truly a force multiplier for modern ethical hacking and security assessment.
Wow, what a deep dive that was into the intricate and sometimes shadowy world of network scanning. We've certainly covered a huge amount of ground today. We went from the basic concept of what scanning is and why it's so strategically crucial for both attackers and defenders, to understanding the fundamental language of TCP flags and the vital three-way handshake. Then we explore the detailed art of host discovery, finding out precisely who's home on the network, using a variety of techniques from ARP to ICMP to TCP probes, followed by peeking inside those active hosts with sophisticated port and service discovery methods, trying every digital door and window, and then uniquely identifying targets through OS fingerprinting, figuring out the very identity of the systems. And we didn't stop there. We even delved into how ethical hackers and attackers meticulously try to scan beyond the watchful eyes of IDS and firewalls, using those clever evasion techniques like fragmentation and decoys. And finally, how AI can automate and accelerate these complex multi-stage tasks. You, our listeners, should now have a much clearer and more strategic picture of how digital detectives gather intelligence on networks, and how absolutely crucial this reconnaissance phase is.
It's been an extensive and really vital journey through this module. And for you, our listener, understanding these methods, whether it's the subtle nuances of a TCP Mammon scan versus a FIN scan, the sheer ingenuity of an IDLE scan, or the strategic choice of when to use an ACK scan over a SYN scan, is truly paramount. It's about knowing not just what is happening or can happen on a network during reconnaissance, but why it matters for security, how these techniques exploit fundamental protocol behaviors, and how you can proactively defend against them or use them responsibly for assessment. We've highlighted the power and versatility of specific tools like Nmap and HB3, and importantly, the new powerful dimension that AI brings to all these techniques, making them more accessible, more efficient, and frankly, more potent than ever before.
Absolutely. Now, this is just one module, Module 3, in the vast CEHv13 curriculum, but reflecting on everything we've discussed today, what stands out to you, our listener, as perhaps the most surprising or valuable insight you've gained? Was it a specific technique like the IDLE scan, the potential of AI, or maybe a defensive consideration you hadn't fully appreciated before?
Indeed. And maybe looking forward, here's a provocative thought to mull over. Given the ever-increasing sophistication of scanning techniques, the continuous development of AI capable of automating and refining them, and the inherent limitations of traditional signature-based detection, how do you think network defenders will need to evolve their strategies? Will simply blocking known bad IPs or simple scan signatures be enough in the long run? How do we move towards building networks that are not just strong, but perhaps truly resilient and inherently harder to scan effectively? Can we make reconnaissance significantly more difficult? Perhaps even approach the idea of an unscannable network, rendering these initial probing efforts less effective? It's a challenging thought experiment for every security professional thinking about the future of defense.
That is excellent food for thought. How do we raise the cost and difficulty of reconnaissance itself? Thank you for joining us on this deep dive into network scanning. Stay curious, keep learning, and keep asking those tough, important questions.
Until next time, keep exploring the hidden layers and complexities of our digital world. Be safe out there.
This has been The Deep Dive.